I'll talk through the solution to question 5 on the examination paper from 2015 for the unit Maths of Graphics and Virtual Environments. So this question is all about the midpoint algorithm, which is used to rasterize circles on a raster array, and you're presented with this diagram which will help you later on in the question. Okay, so part A, with the aid of a diagram, explain how when coordinates of a point on a circle centered at the origin, we can use symmetry to determine the coordinates of 7 other points. Okay, so this is a bit of bookwork from the notes. Okay, so here we have a circle which is we're assuming centered at the origin, and what we're going to do is if we know the position of a pixel in this octant here, so this is our position is given by coordinates xy, and this octant is from the 12 o'clock position around to this position where the line y equals x intersects with the circle. If I know what that position is, these other 7 points around the circle can be found just combinations of plus or minus x plus or minus y, and almost plus or minus y and plus or minus x. Okay, part B, given the error between the point with coordinates xy and a circle at the origin, centered at the origin, radius r is equal to this expression. This is just the Cartesian equation of a circle rearranged. Write down an expression for the initial error. So this is the error between the pixel at the 12 o'clock position, so 0 along the x direction and radius or r up in the y direction, and the midpoint between the pixels to the east and the southeast. Okay, so I'm going to scroll back up to that diagram here. So this is let's say this is our 12 o'clock pixel, okay, and the next pixel along, okay, so this will have the coordinates of 1, because our x coordinate got coordinate 0, and this got the y coordinate of r, so we're looking at, this is our midpoint, so this coordinate will be 1 in the x direction and r minus a half in the y direction. Okay, so that's that error, the next pixel along, minus the error at our 12 o'clock position. Okay, so if we substitute, this is the x value into this, okay, we get 1 squared plus r minus half squared minus r squared, and then we do the same for x equals 0, y equals r into that. Okay, simple bit of algebra, and we get 5 over 4 minus r, and that's our initial error. Okay, part 2, what is the change in errors between the pixels at these midpoints? Okay, so all we do is substitute in these values again into this error formula, and we find the differences. Okay, so quite a bit of algebra here, but eventually you get this expression. Okay, the yi plus yi plus 1 subscript means we don't know what the value of this y coordinate is. It could be one of 2 values, so we have to keep that in. And part 3, write down 2 expressions for the change in error depending on whether the pixel to the east or the southeast was chosen. So what I mean by that is we're assuming this pixel is being illuminated, this is a pixel to the east, and this is a pixel to the southeast. So we have a choice between this pixel and this pixel to move to. Okay, well if the pixel to the east was chosen, we have no change in our y coordinate, so our yi plus 1 is simply yi, and this simplifies to 2xi plus 3. But if the pixel to the southeast was chosen, we move down, so we take 1 away from our y coordinate, and so this yi plus 1 and this this yi plus 1 here and here be replaced by yi minus 1. Again, a bit of algebra, and we get this expression. Okay. So using your answers from part 1 and, well, I should say 2, show how the midpoint algorithm can be written using integer-only arithmetic. Well, these 2 here, which we just derived, they all use integers, but if we scroll back up to the original error, or initial error, epsilon 0, we see we have 5 over 4. Okay, so this is not an integer. So in order to make this an integer, if we multiply throughout by 4, okay, we get integer-only expressions. That's what that question asks. Okay, part C, essentially use the midpoint algorithm. So we've got a circle centered at 10, 10, and our radius is 8, and we need to calculate the coordinates of the pixels in the first octant. Okay, so if r equals 8, then our initial error is 5 minus 4r, which is minus 27. So we start off with the pixel at 0, 8 illuminated, and we look at our error and it's negative, so we go to the east. And because we go to the east, our new error, it changes by 8 times our x coordinate plus 12. Okay, so that's our change in error. So we take our current error and add 8 times x plus 12, which gives us minus 15. Okay, so moving along, so we've gone to the east, so we're now at 1, 8. Our error is still negative, so we go to the east again. And again, we add 8x plus 12, but this time notice that x is now 1. Okay, and that gives us 5. So moving along to the east, we're at 2, x is 2, y is 8. Okay, now our error is positive, so this means we go down to the southeast, so we use this change in error. Okay, so our x coordinate is 2, that comes from there, and our y coordinate is 8, that comes from there. So now the error is minus 23. So we keep going down, using the sign of the error if it's positive or negative to determine whether we go to the east or the southeast. When we get to a stage when our x coordinate is greater than our y coordinate, we stop. Okay, so these are all coordinates of pixels, assuming that the center is centered. The circle is centered at the origin, but it's not. In our case, it's centered at 10, 10. So all we have to do is add 10 to both our x coordinates and our y coordinates to give us the coordinate of the pixels.